Assalamualaikum warahmatullahi wabarakatuh. Today, our group will present about brain tumor MRI scan detection using image recognition. For the introduction, brain tumors pose serious high risk if not detected early. Manual MRI analysis is time-consuming and error-prone, making automation essential. This project developed a convolutional neural network (CNN) to verify MRI scan into four categories: gliomas, magniomas, pituitary tumors, and healthy cases. Seeing advanced technique Using advanced technique, the system enhanced diagnostic accuracy and speed, supporting timely and precise medical decision. Next, for the background, brain tumors are life-threatening if not detected early, and manual MRI analysis is time-consuming and complex. This project develops an AI-driven system using image recognition to identify brain tumors, supporting early diagnosis. Leveraging advancements in medical imaging and AI, the system benefits radiologists and hospital administrators by improving detection accuracy, efficiency, and patient management. Recent studies show CNNs achieving high accuracy rates, 97% in tumor classification, highlighting the potential of advanced AI technique for medical diagnostics.
Next, for the problem statement, it is accurately detecting the brain tumors from the MRI scans is challenging and is also time-consuming and prone to error due to subtle tumor features. Also, the image variation and the data volume. So the current automated solutions face issues like overfitting and limited real-world performance. So in this project, we address these gaps by developing a robust CNN model to improve the diagnostic speed and the accuracy in clinic setting. Now we will move to the next part, which is the research questions and the hypothesis of this project, brain tumor MRI scans detection using image recognition. So for the research question, the first question that we made are the which MRI features contribute the most to accurately distinguishing between tumor types. Second research question, how do specific range of grayscale values and other MRI image features impact the classification of the brain tumors? For the research hypothesis that we made, compared to manual diagnosis, brain tumor identification will be faster and more accurate with the AI-based image recognition technologies.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Daniel bin Muzadi, and I'll be talking about our research objectives, which is first to assess the effectiveness of CNN and advanced segmentation in improving the accuracy and the reliability of automated tumor detection. And next is to investigate how MRI grayscale values and structural features affect brain tumor classification accuracy. Okay, next is the research significance. So first, it enhanced the diagnostic accuracy, where the model improved the reliability of tumor classification, reducing human error and variability in manual diagnosis. So next is accelerate diagnosis, which is by executing the procedure. MRI scan analysis takes a lot of less time, allowing for quicker clinical judgment. Next is assist medical professionals by offering extra insights that complement radiologists and oncologists' expertise, so the system serves as a useful tool. So next is optimize resource application by reducing the load of radiology compartments and increasing patient capacity, hospitals and clinics, so that they can manage their resources.
For this project, we used the brain tumor MRI scans dataset, which we got from Kaggle. The first graph you can see is the class distribution in training dataset. There is a total of 7,223 images. So this distribution include the validation dataset is approximately balanced across all the class. In the training dataset, the highest number of images is glioma with about 1,580 images, while the lowest is pituitary. For the validation dataset, with a total of 1,404 images, the highest is the healthy class with about 450 images, while the lowest is glioma class. So this balanced distribution across both training dataset and validation dataset ensures that the model can learn effectively and reducing the risk of bias towards any particular class. So in this project, the model we use is a convolutional neural network (CNN). As we can see here, the architecture begins with three convolutional layers, each followed by max pooling layer. So this layer apply filter to the input image to detect various features. So this help in reducing the computational complexity and extracting the dominant features. After the convolutional layer, a global average pooling layer is used to reduce each feature map, which helps in reducing the number of parameters and prevent overfitting. So following the pooling layer, a dropout layer is included to randomly set 50% of the input units to zero during training, which making the model more robust. So the model then has a fully connected dense layer with 256 units and ReLU activation, which helps in learning the complex pattern. Finally, the output layer has 4 units with softmax activations, which output the probabilities for each of the 4 class, allowing the model to make a classification decision. So this is the workflow of our project. The first one is the dataset selection. So we select the image dataset and organize into a subfolder, and we load using the image dataset from directory functions, which automatically label images based on the folder names. We use 80-20 split, which is 80% for the training dataset and 20% for the validation dataset and for the testing dataset. For the pre-processing, to prepare for the data before training, we resize all images to 224 times 224 pixels and normalize the pixel values to the range 0, 1 using a rescaling layer. For the model training, we build a CNN with multiple layers and so on. The model was compiled with Adam Optimizer and categorical cross entropy loss. Also, the training was performed using early stopping and learning rate reduction to prevent overfitting and adapt learning rates dynamically. The second last is the model evaluation. We evaluate the model on the using metrics such as accuracy, loss, and confusion metrics were also used to measure how well the model predicted the class labels. And the last one is the result evaluation. We generated various plots to visualize results such as training and validation accuracy or loss curve and confusion metrics. So this visualization provide insights into the dataset balance, highlighting the areas for a potential improvement.
Next, I will continue with the results. This is the training progress over epoch, which has metrics like accuracy, loss, top key accuracy, and learning rates for both training and validation data. The steadily improving accuracy and decreasing loss values indicate that the model effectively learned over time. The graph for accuracy illustrates the training and validation accuracy trends over epoch. The training accuracy increases consistently, while validation accuracy rises initially and stabilizes, showing that the model generalizes well to unseen data. Next, the graph shows the training and validation loss over epochs. Training loss steadily decreases, while validation loss fluctuates slightly but shows a downward trend, indicating that the model minimizes errors as it learns. The discussions, the results show that the model performs well in classifying brain tumors for MRI scans. Training accuracy improves steadily and reached high levels, while validation accuracy increased rapidly before stabilizing. This suggests that the model generalizes well but could still be optimized further to avoid overfitting. The loss plots reveal that training loss consistently decreased, showing that the model learned effectively. However, the validation loss fluctuated in the early stages, like due to variations in the dataset. While the overall trend is positive, this highlight area where the model could be improved, such as better handling of difficult or noisy samples. Overall, the model demonstrates strong potential, but some challenges remain. Adding techniques like better regularization, data augmentation, or trying different learning strategies could help make the model more robust. Future work should focus on refining these aspects and testing with more diverse datasets to ensure reliable performance in real-world scenarios. One area for improvement in the current design of this brain tumor detection project is employing more advanced augmentation techniques such as GANs. which is generative adversarial networks, to create a more balanced dataset. Additionally, while this project used a single model architecture, exploring ensemble learning or hybrid models that combine different neural networks could potentially enhance performance. Moreover, real-time evaluation on MRI scans integrated with medical-grade systems should be considered, and future work could focus on developing deployable solutions. I think that is all from us. Thank you.